Hey there, this is Mrs. Steele, and today we're going to be looking at lesson 2.15, which addresses periodic trends. So please grab your guided note-taking sheet and let's get ready to discuss. So let's begin with, well, what is a trend anyway? Well, a trend indicates that there's some sort of general direction in which something is going to develop or which something is going to change. For example, I may notice that students that are in my first block class tend to be a little quieter and maybe even exhibits evidence of being a little sleepier at first block. But by the time I get to my second block in my fourth block class, I notice that the students are a little bit more awake and more engaged and ready to discuss. So I'm seeing a developing um, um, change that's occurring from one block to another, and it's increasing in activity. Well, why are trends important, or why are they interesting concerning a periodic table? Well, our periodic table consists of over 100 elements. And while when you might look at them from a distance and go, well, they all look kind of gray and kind of rocky looking, that's not actually the case. Elements come in a variety of different forms. Some are solid, some are liquid, some are gases. Some of them are much more varying in colors and have more brilliant colors. Some of them appear more dull, some have luster, some can be flattened easily into sheets, some, on the other hand, may be more brittle. There are all of these unique properties of different elements on the periodic table. And what's amazing, and one would argue miraculous, about our periodic table is that it is organized in such a way that elements that are in the same group or vertical column on the periodic table tend to have very similar properties. However, elements in the same period or row going across from left to right, they differ in their properties. And we notice that they tend to repeat in those properties when you move to the next period. So our goal for the next few days is to explore some of these properties that make individual elements unique and also help to predict how they will react with other elements to make compounds. So what is periodicity? Well, in my opinion, that seems like like a $20 word, but really it's like a $1 concept. So it sounds fancier than what it really means. Periodicity is simply the fact that we observe that properties of elements tend to repeat periodically when we look at the periodic table. So for example, if you look back at the periodic table, you go from left to right, you'll notice the properties tend to vary. Even just the general appearance and how the elements look tends to differ as you move from left to right. However, when I go to the next row on the periodic table, I suddenly see that the property that was similar to the element above it in the same group looks awfully similar. So periodicity is a repeating in property as we go from row to row. Predictability is a kind of comparable term here, but predictability is when you're able to look at where an element is located on the periodic table. For example, I could look and find argon, which is AR, that's atomic number 18 over in the upper right, and I notice, I bet I can tell you a little bit about argon even if I've never seen it before because I see it's in the same group as neon and krypton and xenon. I bet it will behave similar to other elements in the same group. So that's a predictability in its chemical and physical behavior. So, if you're watching this video, there's kind of an assumption that you've already completed the coulombic attraction Pogel activity during class. And most likely it took you an average of about 20 minutes to complete it as well as discuss it with your classmates. So as we watch this video, we will add on to what I already assume that you have explored during class time. So let's begin. Well, the easiest way to observe periodic trends is to study the first 18 elements on the periodic table. So specifically, I recommend that you study from hydrogen, which is atomic number 1, over to argon, which is atomic number 18, and you will see some very evident properties that these elements have, and you'll see some similarities among elements, and you'll see some drastic differences with other elements. So if we look at just the first 18 elements, I can visibly see right here some very distinct properties. For example, it appears that the electrons, the valence electrons I should say, which are the outermost electrons, the ones that are on the outermost occupied energy level, they differ from row to row or period to period. Group 1, the valence electrons are on energy level 1. For period 1, the valence electrons are on energy level 1. On period 2, the outermost electrons are occupying energy level 2. And for period 3, the valence electrons are occupying energy level 3. That in and of itself is very important to know. Okay. Now here's the periodic table, just so that you can have an example of how those atomic models that we just looked at fit in with an actual periodic table that you all should have copies of. Okay. Now I hope that you noticed a predictable pattern here. Elements that are in group 1 have 1 valence electron. Elements in group 2 have 2 valence electrons. Elements in group 3, which is sometimes called group 13, have 3 valence electrons. Let's circle those so you see them. 1, 2, 3. And so forth. 4 valence electrons for the carbon group, 5 valence electrons for the nitrogen group, 6 valence electrons for the oxygen group, 7 valence electrons for the group that begins with fluorine. Those are called the halogens because they form salts. They're salt formers. And for group 8, or sometimes called 18, they typically have 8 valence electrons, with the exception of helium, which is full with just 2 valence electrons. So helium is an exception, and it has just 2 valence electrons. If you didn't know that, I highly recommend that you jot that down on your notes for today. Okay. So once again, a big takeaway from our POGL assignment was that the outermost electrons that are in the outermost occupied energy level are called the valence electrons. And these electrons are available to be lost, gained, or shared by atoms, and so that actually plays a key role in chemical reactions, which we will talk about later this week. Okay. Now, when we talk about valence electrons, also note that we're going to focus only on the S and P electrons. When you enter into the D sublevel, it gets a little bit more confusing. And so to save ourselves some of the hassle of trying to discuss all the subtle nuance of the D block elements, we will focus only on what we call the main group elements, which are in the S and P sublevels. So keep that in mind when we're counting valence electrons. All right, so let's go to our note-taking guide. You should have a fill-in-the-blank note-taking guide that has some learning targets up at the top, such as defining valence electron, which we just did, as well as defining effective nuclear charge, which we are about to do, defining shielding, and several other learning targets as well. I'd like to note that there are several important vocabulary terms that you need to be familiar with. So look at your note-taking guide and make sure that you are familiar with those. What we will do for this first part of the lesson is just complete the first parts of your note-taking guide. And most likely we'll go into a part 2 of this video, and I'll post that for you guys on our learning management system. So let's begin. Coulombic attraction. What's the basic premise and in the important terms? Well, based on the POGL, a coulombic attraction is the attraction between oppositely charged particles. So let's fill that in. The coulombic attraction is the attraction between oppositely charged particles. So we're going to be interested in the attraction between the protons in the nucleus of the atom and the surrounding electrons. Pause. Does that make sense? Protons are positive, and so they would be attracted to electrons, which are negative. Opposites attract when we're talking about electromagnetism. Okay, let's continue reading. Specifically, we will be looking at not any electrons, but valence electrons, the ones that are on the outermost energy level of that atom. The outermost, and I'm going to actually include an extra word in there, especially for pre-AP, occupied energy level. Arguably, we could say that any element or any atom of an element could have um, tons of energy levels, but when we're referring to valence electrons, we mean the outermost occupied energy level, it meaning the one that has electrons on it that is farthest from the nucleus. Let's go to the second bullet. Coulombic attraction between protons and valence electrons in an atom is measured in terms of effective nuclear charge. Fancy word again. Another one of those $50 words. What's the deal with those? Well, nuclear means in the nucleus. What's in the nucleus again? Oh yeah, the protons. We set that up here. The protons are in the nucleus. So we know that effective nuclear charge has to do with the pull or the pull on the electrons that is caused by the protons that are in the nucleus. Effective literally means like to what extent or to what effect it has on the electrons, specifically the valence electrons. It is abbreviated ZEFF, Z standing for the nucleus, and then the EFF subscript represents is an abbreviation for the word effective. So we're saying the effective nuclear charge. If you ever hear somebody say ZFF or ZEF, there are three factors that influence this effective nuclear charge, and so we'll dive into that in just a second. So just to be clear, the effective nuclear charge is the force of attraction the electron experiences from the nucleus. So on your guided notes, you're asked a couple questions. Well, how does the atomic structure change? Look at these four elements here: lithium, beryllium, boron, carbon. According to their atomic number, they have 3, 4, 5, and 6 protons respectively, and those protons are located in the nucleus in the center of the atom. Well, according to the Pogel assignment, the more protons there are in the nucleus, the greater the effective nuclear charge, right? So we would predict that carbon will have a stronger pull on its valence electrons than lithium, even though both of them have the same number of energy levels. Carbon has a greater effective nuclear charge. Going down a group, we notice that, for example, hydrogen, lithium, and sodium all have one valence electron. I wonder what's going to happen with this then. Well, something important to understand about effective nuclear charge is that effective nuclear charge is calculated in this way, and I highly recommend that you guys jot this down so you can calculate it properly. It is calculated as the number of protons minus the number of core electrons, which are the non-valence electrons, anything but the valence electrons. So, for example, if I look at hydrogen, the effective nuclear charge for hydrogen would be, well, how many protons does hydrogen have? 1. How many non-valence electrons does hydrogen have? 0. So what's the difference? +1. It has an effective nuclear charge of +1. Let's try lithium. Lithium has an effective nuclear charge of, 3 protons minus 2 core electrons, which are on this level here, equals a +1 overall effective nuclear charge. Let's try sodium. Sodium has, I believe, 11 valence electrons. Let me double check that on my periodic table. Correct. Minus 10 core electrons, which mean non-valence, and you get a difference of +1 once again. So let's summarize here, and we'll be done with our first video. Across a period, the number of protons increases. The distance remains the same from the nucleus to the valence electrons, but the effective nuclear charge is going to increase due to the number of protons increasing. In contrast, down in group, you're going to include an additional occupied energy level each time you move down the periodic table. Therefore, the distance between the nucleus and the valence electrons increases, shielding increases, meaning there's more core electrons, and the effective nuclear charge decreases.